Well, I didn't mean for that to happen. Sorry you heard an echo for a split second. I was monitoring my audio and just seeing what would happen and if my levels are good. I think I'm talking a little bit too loud. Let me just turn it down a little. But sorry for the dark atmosphere I've created. I tried to go for the CrowdSec vibe of having one side like golden. But if I turn on my light, I have too much drop shadow, so I look like I'm, physically ill. So how are we all doing on this Thursday? It's community office hours, if you don't know already. And we have this monthly office hours where we just join together and talk about a cool topic. And yeah, that's pretty much it. I will be waiting 2 more minutes just so everyone can get in, because we say 5 p.m. but obviously I know you've been enjoying the relaxing sounds of the waiting room. But I'm just also going to see if the community manager Yoda and everyone's happy with the audio, and they will tell me if everything's okay. Everything good. I know there's a 15-second delay, so I'm gonna get like a text message in like 15 seconds when everything's so good. But everything should be fine and dandy. But let's wait another 2 minutes. So how is everybody doing? We've got a few people in here, but this is the beauty of doing it on YouTube instead of on a platform like Livestorm. Anyone can just join randomly, pop up and see what we are doing. So yeah, if you don't know me, I know I'm looking to the left because that's where the stream is, and you're looking here, so I look kind of weird just looking over to the thing. Look, I'm staring into like nothingness. But yeah, if you don't know who I am, I'm Lawrence Jones. I'm the head of professional services here at CrowdSec. That just entails I work with clients and the community as well. You may see me on platforms under the pseudonym of I am Loss. So if you're talking to that guy, that's me. So, but right, should we crack on? Cool. I've been working on some of these nice little layouts for the streams, because normally it would just be me with a CrowdSec background and look kind of boring. But you can see all of our social medias at the bottom, so go check us out, follow us on those platforms, and you can stay up to the latest and greatest news that we are working on. So let's switch over to the main display. Ooh, some more main display, some more information. Look, this is pretty good. Snazzy. Am I right? But yeah, so the topic of today is we're talking about open source HAProxy-Native security. And the reason that we're calling this HAProxy-Native security will be very apparent in this live stream, because we did have an integration beforehand, but I'm getting a little bit too far ahead of myself. So let's go on to the first slide. So with many of my webinars, I like to set out like introduction and objectives so we can all be on the same page of what we're going to learn in this talk. Now, I'm not going to lie to you, this is a very technical webinar. I'm not going to go over the steps of installing the component into HAProxy and all that stuff, because that's the whole reason for documentation. The reason that I wanted to go into a technical webinar was just to give you a glimpse of the code and the background, what we do as a company to obviously support these types of technologies, and just overall just enlighten your knowledge of how all these systems work together. So why HAProxy? Why did we want to support HAProxy? Well, it's the go-to reverse proxy, and it has been winning many awards lately, especially by G2 standard. Because the team over in HAProxy, who has the founder of HAProxy has quite like knowledge of CrowdSec, and he supported us personally, as in like he's supported the projects as in like direct communications, so he knows of CrowdSec. And we liked their philosophy of that if their program's going to run, it needs to be supported across, you know, minimalist environments, which we obviously try to do as well. So yeah, HAProxy is the go-to choice for teams that need the speed, control, and reliability at the edge of their network. Most likely, if you've ever come in contact with it, it's normally acting as the main access into a network, and it's frequently there where they would enforce the security decisions, either at the TCP level, where it's just a TCP load balancer to other web servers downstream, or if it is the reverse proxy itself into the network. I've seen some really crazy setups with HAProxy being, you know, HAProxy into HAProxy into HAProxy. It can all obviously get very complex so fast. So what are our objectives during this webinar? Well, I'd like to give a brief introduction to what is CrowdSec, because sometimes people may stumble upon this video and not even know who we are. Give a brief background on our Lua integration. So if we did have a support for it before, but it was all written in Lua, and I'll give the pros and cons and obviously why we switched to a different architecture for our integration. And what is SPO, SPOP, and SPOA? Well, HAProxy has the same acronyms as we do. We have 4-letter acronyms, and they have these 4-letter acronyms, and I'll go through what each piece of the puzzle is and how it all fits together, so you can get this whole technical knowledge of when you're using SPO, what does it actually entail? Because out there on the internet, there's not really many resources that you can find on this, and when I was first creating this integration, I found it a hard time, and I just wanted to give back and give a single overview. And then the SPO component itself, we'll be diving into a little bit of the code, not obviously the full code because it's thousands of lines long, but I'll just give you like the brief objectives of which component is in charge of what and what it actually does. So let's jump straight in. So if you've never heard of CrowdSec, it's an open source security engine which can detect malicious behavior. So we always get asked, well, a malicious behavior, what is that? Well, in CrowdSec, we primarily read from logs at the very start of our developing it, and now we also have a WAF component as well. Once it detects a bad behavior, it can then do a block, a capture challenge, or even rate limiting in some certain integrations, most likely the WordPress one. And this is how the engine works, just in a clear overview in the middle. It's a little bit small now since I've realized that I've done all this little layout thing, but basically the security engine's in the middle next to your logs, and then it basically instructs the remediation component, which was the name of bouncers before we changed it. And this is where HAProxy would be in the scope of where the ecosystem is. We then have the central API in the top right hand corner. This central API is basically where you get your community block list from, and where you send your signals when you detect a malicious behavior. And that's one thing I failed to put on this slide, that CrowdSec is obviously primarily about community threat intelligence, that we share signals about bad behaviors we see, and then obviously the benefit of that is that the whole network gets to we get to map out all these malicious trends that are happening, as well as you get a community block list included. So our Lua integration. So when we first started looking at being embedded inside HAProxy, we first started with the Lua integration, and it wasn't the best because it's Lua. Not that I don't like one index-based languages, but Lua obviously has its limitations. It's a runtime language, so you can fall into the pitfall of not having type safety and all of these little things that you may not check for in Lua, because it's no typing. So a string may be nil, but you don't check it, so hey, you get a panic at the runtime. So we originally shipped it, it worked, but we had two major constraints that stopped us from basically developing it any further. That the startup time when the Lua came up, it could take at least 1 to 2 minutes to download every decision, depending on how many you had in your CrowdSec like inside the database. So we try to look at doing multi-threading and stuff like that, but what you'll hit is that there is no thread safety inside maps. So they were all fighting to put in the stuff at the same time if you're using like a shared map between them, and it was just overall just not a fun time. And also as well, when you're inside an organization which may be deploying, you know, HAProxy in a Kubernetes fashion where it needs to spin up and spin down, you don't want to be waiting 2 minutes to block an IP address that's coming into your infrastructure, because you're basically saying, hey, you can attack me freely for 2 minutes, and then when this infrastructure goes away, then obviously that's it. And then we also had HAProxy version compatibility with the certain code not running on certain versions, and that's just because internally inside HAProxy it changed the Lua between certain versions. And like it says at the bottom, we had a customer who had a hard time running mixed fleets because they didn't upgrade their HAProxy across all versions at the same time, and they would hit this constraint and it would cause a really bad time. So what is SPO, SPOP and SPOA? These are the three acronyms that you'll see mostly when you're talking about integrating into HAProxy. So if you use your favorite search engine to search HAProxy SPO, SPOE, that's the main page that you'll see up, but there is these three acronyms inside of the blog article. So the SPO stands for Stream Processing Offload Engine, and it's basically a way for HAProxy to delegate or send messages to an agent. And well, I'll go over the three acronyms first. So SPO is the engine that actually runs inside of HAProxy itself, and we'll get into the configuration in a minute. SPOP is the protocol used to transfer messages between HAProxy and the agent. We'll also dive into a TCP dump so you can see actually the structure of it. And SPO itself is actually the agent. So that's why you'll see projects call themselves, you know, CrowdSec SPOA or Karaza SPOA, because the actual agent itself is a SPOA, not an SPOE, because that's the engine inside HAProxy itself. And yeah, the agent itself receives the messages, does the processing that it needs to do, or the checks that it needs to do, and then it will respond to HAProxy with data points. And those data points is what you can use inside your filter mechanisms. So yeah, you attach the filter to the front end of the back end. It receives data that you can access inside of transaction variables, and you can do certain stuff with it. So you can basically say, is this remediation for this IP address a ban? Okay, we'll reply with a ban page. Oh, it's a ban, we'll just redirect it to this subdomain instead of going to the actual backend. These are just examples that you can do at this level. Yeah, so the SPO itself has this configuration. So on the right hand side is basically our SPO config. And I think there is a way for me to do a highlighting, but I haven't actually tried it before. So let me just have a laser pointer. Okay. Ooh, look at this little laser pointer. That's cool. Okay. So inside the SPO itself, this top bit here defines the name of the SPO. So obviously we got to call it CrowdSec. There's no other name for it. And then underneath we define what the agent is. Inside the agent, there is the messages. These messages have to align with the SPO message that's down here. So you can see that we have a SPO message called CrowdSec TCP, and we define it as a message here. The reason that there's two different things as a messages and a groups, I'll come into in a second, but I just want to focus on just this one message for now, and then we'll talk about what is a group and what it actually does. So on this SPO message, we can see here that there is a definition of some arguments. These arguments are basically the data points that will be passed to the SPOA under these key names. So you can see here that we have an ID prop, which is the unique ID of the request that's coming in, because HAProxy has the ability to tag requests with a unique ID for tracing purposes. So we use this as a way to, if you pass this back, we log it out in debug mode, so you can see which request came in, and you can basically connect the dots between the SPOA logs and HAProxy's logs, just for tracing purposes. We also pass in the source IP of the request, or the TCP request in this case, and the port which was the request was sent from on the client side. However, you can see here that there's an event hook. Now this is where SPO defines when this event will fire. So on client session is whenever a TCP connection has created from a client to HAProxy, this event will fire. Now there's one caveat with this. If you have an upstream proxy like Cloudflare or CDN or something like that, then obviously you're going to get the wrong IP address here, because you're only going to see Cloudflare's IP at this TCP layer. So this is where we have these SPO groups. So a group is a way to define a message inside of the group where you can specifically trigger it at a certain time inside the request flow. So typically in this left hand side where you have this front end test, and you know, this is just garbage data, you will have, like, you know, get the real IP from the headers and set the source IP to that IP address. This is where you can then say to it, okay, after I've done correctly setting the source IP, I then want to trigger the SPO group called CrowdSec HTTP body or CrowdSec HTTP nobody. This will then, the SPO will then see that the source IP has changed, and it will go and do another IP lookup and see if there is a new remediation that it needs to do. I hope that wasn't too much information, but it's just good to get the baseline of the technical details of how, you know, HAProxy has this configuration and how it interacts with the whole stack. So we have some processing timeouts that we set here. So this is pretty much just, you know, a connection between HAProxy and the SPO. How long should that take? How long should it take before an idle connection should be pruned out of the connection pool? And then how long should processing of the request on the SPO side take before we class it as a failure to respond? You'll need to tune these options to what you like to do, because obviously 500 milliseconds doesn't seem that long, and in our own testing the SPOA responds typically within 100 milliseconds. But if you've either got technical limitations, or, you know, the SPO where it's running is further away from the actual HAProxy itself, then you'll just need to tweak these knobs just to make sure that everything, so you don't cause too much impact on the client side, for example. So the SPO message here, CrowdSec HTTP body and CrowdSec HTTP nobody, they're pretty much the same invocation on the agent side. The only difference is that we don't define the body in one and we define the body in another. And this is particularly important when it comes to the AppSec, which is the WAF feature of the SPOA. When you're sending the body across the wire, you're limited by the tune.buff size, if there's any HAProxy people in here. So you cannot send more than 64 kilobits, I think it is, that across a message frame. And if you do go over that limit, then the rest of it is just spliced off and you lose that data, as in like the transit of the data, not the data to the back end. And inside this send SPO groups, you will basically send across the remediation that we had before. So this here is the remediation that the TCP request had. We then send across the unique ID, the source IP, all the headers, the bodies, and everything. Or nobody if you choose to do the nobody route. Yeah, and this will basically pass all those data points to the SPOA. The SPOA will then do its magic, and then it will respond to the HAProxy with, you know, transaction CrowdSec.remediation, and you basically do like a string match on that. So when we do send these these values across the wire, what does it actually look like? Well, I've got this lovely TCP dump for you of the thing, and I can just notice that my camera's in the way of the one thing that I wanted to show you, but hey, I did this live. So SPOP is basically the protocol that HAProxy uses between HAProxy and the agent itself. In the specification for the TCP data that gets sent across the wire, everything is called a frame. So a frame is basically a packet that gets sent across, and you should basically read from the frame length to the end of the frame length. So the first 4 bytes that is always sent across the wire is how big the frame actually is. You then read that amount, and then the next one will be the next frame length and then the frame buffer. This is standard if you have your own custom TCP protocol, where you need to obviously make sure that things are aligned in the same way, because if not, if you overread one frame, you'll then splice into data that shouldn't have been read from this frame buffer. So what is a frame? So a frame is made up of the first byte being the type of the frame, a little bit of metadata about the frame, and then the frame payload. The metadata about the frame is 4 bytes of any of the flags, the stream ID of the request that came in, and the frame ID. I know this is a lot of information, but it's interesting to see how HAProxy actually implemented their own custom TCP protocol and what caveats can happen from having this. E.g., they mentioned, the tune.buff size, that you can only have such a big buffer before obviously you're going to run into some limitations on your side, because you don't want to handle all the data in memory, because you're gonna hit obviously memory consumption limits. And on the right hand side, this is just basically a TCP dump of seeing what's actually sent across the wire, and you can see here that there is a the first couple of frames are basically sending across a hello and an ACK from the agent to the HAProxy, so it knows that it's alive and it can connect to it. It will then, HAProxy then sends across the options which it supports, because the SPOP protocol has evolved over time and there's been new additions, so it needs to figure out if the agent can support these types of things before it knows how to send the data properly. And on this layer here, which is being covered by my face, but if I just try to do if I just undo this for a second, yeah, so you can see here that the first request that got sent across is the CrowdSec-TCP the CrowdSec-TCP message. So you can see in here that you can actually read the data that's being sent across. So it said, okay, this is the message CrowdSec-TCP, here's the ID of the request, here's the source IP, and then the source port and that lot. But obviously it's not showing that full data inside the request. But here you can see that the data is easy to read, and this just helps you with your debugging the actual protocol and seeing what's getting sent across the wire. So on the agent side, so this is a really heavily slimmed down version of the SPOA, and this is the custom agent that handles the SPO messages. So HAProxy will send across a frame with the name, the CrowdSec-TCP that you saw, and we have this constant inside Go called message CrowdSec-TCP, and it's a byte buffer of the string CrowdSec-TCP. When it receives the message, it will then get the name by the bytes, and then it will do a compare to say, is the incoming message matching CrowdSec-TCP? If so, we'll then invoke this function called handle TCP request. And the reason is because obviously CrowdSec-TCP only has 3 data points sent across the wire, where CrowdSec HTTP, body and nobody, has loads of data points that we need to pass out and handle differently. And down here you can see that there is just a placeholder for the handle TCP in the context, but it's just to give you the idea of that when a message comes across the wire, we then grab the message, we compare it and say, okay, it's a TCP request. We need to go and do these things, respond in this way, and then HAProxy can do the actual enforcement on its side. So as I mentioned, we have 3 message names that we support: CrowdSec TCP, and then CrowdSec HTTP body and HTTP no body, which is just simple things. And yeah, and also just for logging purposes, we have a trace logger at the end that if you somehow put a message that we don't know how to handle, then we just log it because we can't do anything with a name that we don't know. Obviously, this creates a caveat that when we do update the names of the messages, so in version 0.2.1 and below, we had CrowdSec TCP and CrowdSec HTTP. That was it. So when you upgrade the SPO, you need to also make sure that you're running the latest SPO configuration, because if the message names are not in sync between the agent and the SPO configuration, then you will ultimately send across a message name that we do not know how to handle, because the versions and the SPO configuration are all out of sync, basically. So what is the CrowdSec SPOA? Well, the CrowdSec SPOA, I've ripped this straight from the GitHub README, but it's basically a real-time minimal latency, which we will go into detail about the minimal latency. And it basically does, it contacts the CrowdSec LAPI to get the active decisions on the IP addresses, and then it will respond to HAProxy with variables that you can use inside of the template or the HAProxy configuration to do like render a ban template, render a capture challenge, or just, you know, cut the TCP connection early and just don't care about the clients at all. So the reason that we have CrowdSec TCP is because if you're using it as a layer 4 proxy, you may want to enforce earlier than down the chain. We have a host aware behavior, which I go into later on in the slides, but because MSPs and hosters who have, you know, multiple clients, you may have to support multiple different configurations. Let's say a client, if they get a ban and they don't want to enforce, or they want to redirect to a different subdomain, you can do that. Or if you, let's say, have a capture template, so there's a capture decision, but a user doesn't configure a capture page, you can then, you know, not render a ban page and just let the decision fly through, for example. There's multiple different ways you can do it with this, but I'll go into that a little bit different. But yeah, the inbuilt captures that we support are HCapture, reCapture, and turnstile, the same 3 that we support with all of the web servers that we support. And we are working actively to support a custom capture provider, similar to how Traffic and Max and the team supported WicketKeeper. We're also going to support that down the line, but hopefully that won't be too far away. Because we want to be minimum latency as possible, we have memory efficient dataset module that we've created, and it uses a whole bunch of techniques to make sure that we don't block the reading path for too long. So there is multiple different things, but I'll go into that a little bit later. But yeah, visual debugging, and then we also have support for GeoIP as well. So you can tag on the max mind that comes from CrowdSec, and you can have those GeoIP lookups inside HAProxy. So if you want to do, let's say, GeoIP blocking inside HAProxy, you don't need to configure MaxMind with HAProxy, even though it's natively supported anyways. And the one good thing about doing it with CrowdSec is that because they use the same MaxMind database, you can make sure that they're totally in sync with each other. So if there's a remediation on a country, the IP that gets looked up to the same country will always be consistent. And yeah, in 0.3 we've just released the AppSec forwarding capabilities, so you can now turn your HAProxy into a WAF powered by CrowdSec. So this is now getting into technical under the hood stuff. So we have a SDK library called Go CS Bouncer. What this this library does, obviously it's got the old naming of a bouncer, but it contacts the CrowdSec LAPI. So you can see in this diagram to the right hand side that it fetches the new decisions, it gets the data back, and then it applies the updates to decision dataset. So the decision dataset is a module that I've been working on for some time, and this will basically an in-memory structure to do ultra-fast lookups. And this happens every 10 seconds by default, but you can make it shorter or longer depending on how frequently you want the SPOA to update itself. And the one good thing about being written in Go is that it's 10 times faster than Lua. So I currently have a HAProxy-Native machine out on the internet, and currently with 180,000 decisions, it takes less than 2 seconds to start up. So you can make sure that if SPO's already running, HAProxy doesn't matter because it will just contact this with the data points. So you can see how quickly we've managed to speed up the enforcement on that side. And this is what the decision dataset looks like. So again, it's very, very abbreviated code. This is a lot more code, but inside the dataset itself, there is 3 sets. There's the country name set, there's the IP map, and there's a thing called a range set. So there's a reason why we split it down into multiple different data structures. But the long and short of it is that when we were testing out different ways to hold IP addresses in memory, we did try to do like a tree implementation, which I'll get into a tree later on. And we just saw that it causes way too much memory usage for very little benefit. Because when you go into a map, it's just like a lookup straight into the map. Obviously, it's got to internally go and look up the elements inside the map, but it will be way quicker than, way less resource intensive than holding it actually in the data structure. So yeah, exact IPs live in the IP map for the cheapest possible map. CDAT based decisions, so these are range remediations, live in the range set, and we currently use an implementation called BART radix tree, which solves one of the problems that we had when the first implementation, which I'll go over in a sec. So check IP drives the lookup flow. So we receive an IP into the check IP function. The first thing we do is make sure that it's a valid IP. This is just a developer catch, just in case we're an idiot and we pass in the wrong IP or pass wrong values in. We then do an IP map contains, which checks if the IP contains in the map. You can see here that these are the Prometheus timers that we have just to see how long it takes to do, because it's useful for users if they actually know if they're getting consistent lookups. If we find the IP within the decision map, then we just return the remediation and the origin of where this came from. So an origin inside CrowdSec is where the decision happened from. So the main ones that we have are like CAPI, CrowdSec, which is the security engine, and then we have a new one called lists. So these are the block lists that you download or come from the console. If we don't find anything, we then hop onto the next row, which is basically doing a range remediation and checking that, and then ultimately we always return a remediation and an origin, because by default the remediation that gets returned from the first IP map check is an allow remediation. And then further in the SPO code, we do GWare IP lookups, and then we do then check if there's anything in the country map later. But the one thing to point out here is that all these data structures use a copy and write mechanic. So reads are always available, no matter if there's like a big massive update coming in from the CrowdSec security engine. Because what we do is, let's say we have an IP map here that's got 50,000 entries, and then we got a decision come in saying, hey, there's 10,000 more IPs that I need you to add, or I need you to delete 5,000 of them. Just an example of Delta. We then copy these 50,000 IPs to a new map of itself. And then we then update this copy. And then inside Go, you can basically say, okay, I'm ready now to replace the original 50,000 that we had with this new updated delta. Okay, I'm going to wait for the SPO to stop reading as much. And then the internals of Go will basically, I forgot what it's called, like system, like timings. And when it's allowed to lock and do a replace, it will replace the whole data structure at once. So this is just a way that SPO can always continuously read, and it's never blocked on the hot path. So we always return a remediation. Beforehand, we were not doing this copy and write mechanic. And the main problem that we had is that, let's say we got a massive change, like 100,000+ decisions that came in. SPO would just block and stop responding to messages. And it's like, well, we technically already still have the data present, and we should always be responding with something, even if it's just a remediation allow. Like, we don't want people to have to make a decision saying, okay, I don't know what this remediation is. An error happened, it timed out. So do I just drop the request because I don't know if it's good or not? Which, that's why ultimately we changed to this copy and write mechanic, just to make sure that we never block the hot path at all. And now we can jump into what actually is an IP map and all this kind of stuff. So you can see here that if you've ever used Go before, it's a sync.map. It's typical, just to make sure that it's thread safe across the thing. We create a new IP map. It has an alias just for logging purposes, so people can actually see inside the log what the IP map is doing when it's in debug or in trace mode. It has two functions for the decisions called add batch, remove batch, and this is pretty much just a stream of decisions that we need to add and remove. The reason that we have a batching operation is just so we can do it over more cores. The contains function, as you saw, was the one that's used to check if the IP is in the map. I've just obfuscated the code because I think I always try to use like functional names, so we don't actually need to know the logic inside, but contains just checks if it's inside the map. If it is, it returns all these data. And then has remediation is simply just a safety check. When we're first receiving all the decisions, we need to actually know if we need to change the origin of a request. Is this remediation that we're getting a new, like brand new, or is it that we've already got the remediation and the origin just needs to be updated? Then we could just do a simple, change the origin. We don't need to do a full, remove the entry, re-add it again and stuff like that. And then the count at the bottom is just for metrics, just to see how big the data sets are in the thing. And this is the more interesting one, because this was a 0.2 update that we did. So we have a range set, and it uses a module called BART. So you won't find it if you just search on GitHub BART, because there's many projects that use the same name, especially ones that are tied to The Simpsons. But if you just search your search engine BART Golang, you'll find the project. But BART stands for Balance Art Routing Table. It's a way for you to store data in a tree implementation, which next slide I'll say what a tree is. If you like, I'm not a data scientist and I'm not a computer software engineering guy, so I spent a lot of time learning this stuff, so I thought I'd give a little bit back. But it basically implements the same interface across the structure. So it has the same new BART, add batch, remove batch, takes in the IP address and sees if it's inside the range, and returns all the same data points as the ones beforehand. And then has remediation and get origin for a remediation, all the same details. And this is quite useful. So what is BART itself? Well, it's a multi-bit radix tree. So inside, well, let's think of a point of what is an IP address. Well, IPv4, it's number dot number dot number dot. So it's obviously bits of an address. And these bits, when you're searching for them, they're always in 8-bit increments. So that's why you always, a full IP address is /32, because you got 8, 8, 8, 8, 8, 16, 24, 32. So if you want to say an IP address is like a full address, 192.168.11/32, that's the full address, because you're defining the 32 bits of an address space. Now, what BART does in particular is when you give it a range remediation, it will break down the range by the 8-bit increments, and it will allow you to walk the path of that. Now, you might say, well, Golang has a net IP prefix. Why can't I just use that? Well, if you're storing CEDAR ranges inside a loop, then you're going to hit 2 problems really fast. The size of the array will cost you, because obviously you're iterating over those elements. So if you have, let's say, 100 to 500 elements, it's going to get slower and slower and slower. Inside programming, you might see this called the O of n. So n being the number of elements inside of the array. So obviously as n gets bigger, the processing will also take longer and longer time. The second problem is that this time is going to affect every single request that comes in, because we have to check every single array, or well, every single range, to see if it's inside any of them. So you'll fall into the trap of a miss will be more expensive than an actual match. So let's say in the order of the thing, you've got 10, 008, for example, and the second element is 192.168, whatever, just for purely hypothetical things. So as we check the first one, that will match straight away. We don't need to check the second one. But if something comes in and has to check all 2, 3 elements, your misses will start, causing you a lot of pain, and it will slow down things quite a lot. So what BART does is that it splits it into O of k. So this is another data science thing, where k is the length of the bit. So you can see here on here, so you can see that 8, 16, and 24. So depending on how many bits they are, your lookups will always be the consistent timings. You guys can talk in the chat if it's going over your head, because it went over my head when I first started learning about data structures and everything like this. So you can see here that we have a root element, which will be the first, which is 10. We'll check this. We first check the 10, and then we check the next octet, which will be the 1, and then we check the next octet, which is the 2. What this will allow us to do as well is longest prefix match. So when you go through the elements and check them in order in the old style of code, let's say you have 10.08 as the first element and 10.016. Well, if you're just looping over these and you match the first one, how do you know you need to go check the second one? Well, you just take the first one and just say, okay, that's the remediation. What BART allows us to do is have these multi-level, different remediations at different scopes and different bit arrays, and you can get basically really fine-grained things. So if you were having a DDoS attack and you have CrowdSec issuing all of these decisions for these different types of ranges, you can basically mitigate it in all the different ways. So you can say a /31 has a ban or a capture just to try and catch the pairs, and then /28 has a ban just to override these ones. And it allows you these fine tuning of these tweaking of knobs just to make sure that you can have all of these things covered. So when you get to later on down the line, it's quite good in that regard. And yeah, consistent low latency, because the lookups are always how many bits are inside of an address, and that's always consistent. It's memory efficient for the storage, because you split down the CDRAT into the actual bits itself, so it can walk through the thing. And then It works quite well with the snapshot, you know, the copy and write stuff, because we basically take a copy of the data set, do all the stuff, and then put it back into memory. But I'm just going to take a swig of water. Awesome. All right. And then I don't know why I put this slide in there, because this one's quite the most boring data set. But basically, we just store strings of the two country character code, and then when we do a GUIP lookup, we check if the 2-letter code is inside the map and return the origin and remediation. It's just a way of us supporting, you know, country bands inside CrowdSec. And this is how it's provided with the country code. So we have a geo provider inside of Ing, which supports MaxMind, and it basically bootstraps the GUIP and gets the ISO 2 character code from the IP address. As stated beforehand, it allows you to use the same GUIP module that's CrowdSec is using. So you can ensure that if you do a GUIP lookup in CrowdSec to do a remediation, then that same IP will be the same country when it comes back inside of HAProxy SPOA. Now this is where, especially for hosters and MSPs, this is where the main draw is for these types of configuration. So we have these data points called hosts. What these hosts are is basically the top level domain that comes in. So do you know when you curl example.com, you send a host header that has this information here. What this allows you to do is have configuration per host. You can either use the host directory, which is basically a place on disk where you hold all the configuration files, or you can define it inside of the main configuration file of the SPOA. It allows you to set up, let's say, a capture provider for the host. It allows you to override the default remediation if there's a remediation that it doesn't know how to handle. And it allows you to do cool stuff like this at the bottom, where you have a catch-all. So if we go through these domains and we end up on the last one, especially for hosters in particular, because there may be clients or users of your clients that get through to the ban page and they have no idea who to contact to get through, and they might just leave a bad review on your client's website saying, I couldn't get through, there was something about CrowdSec and I don't know why I'm not allowed to visit this website. This allows you to make sure that your clients have like a way or your clients have some way to contact for help, because if not, it's not really a good user experience if they're just stuck staring at a CrowdSec ban page without a way to get back. These host keys are basically a match on them, so you can use star.domain.tld or xyz.domain.tld. You can use anything that will match a normally thing. So if you do like a regex expression, that's what they are, and it allows you to basically, like I said, do a bunch of configurations. So you can use, let's say, turnstar for one domain, and then you can use hcapture for another. So it allows you to have all these these things that you can tweak. And this is the path I wanted to take when I first had a look at it, because our old Lua integration, you just set up one thing once and you didn't really have this opportunity to, let's say, tweak these little things because especially for hosters that are using HAProxy, you need to have all of these configuration options to be able to support your clients. And that's pretty much the whole webinar. I'm not, as I said in the preface, I'm not going to show you how to deploy it because we already have documentation for that. We support all the major distributions, so you can, well, except for Windows, but I don't know many people who are running HAProxy on Windows, but I've still yet to be proven wrong because some guy called me out on Reddit for not supporting Windows, and I said I didn't realize people were running HAProxy on Windows, and he said no, neither do I, and I was like, well, what are you complaining about then? I don't really know. But the QR code will take you to the documentation, as well as if you go to docs.crowdset.net. If you search SPOA in the search bar that comes up, you'll land on the documentation itself. But yeah, if anybody has any questions, remarks, or anything on what I've shown, I will be gladly answer them. As well as if you give the project a go and you encounter any issues, don't hesitate to open up a GitHub issue. We're slowly growing. There's about 100 people, or well, 100 instances of SPOA out there at the moment. So it's not obviously our main thing, but it's still in beta. So we're still working out all of the rough edge cases. Okay, let's look at the laser. Wow. Okay. Yeah. So, just a quick reminder: if you check us out on the socials, I can never get the right angle. Check us on the socials on the left-hand side. You can join us on Discord. You can check us out on GitHub. You can check us out on Twitter. Somebody stole the crowd security one before us, and we can't get it. So now that's why it's this weird _ one. You can check us out on LinkedIn, and also obviously you're on the platform itself. You can check us out on YouTube. Give us a subscribe and like on the video itself. It helps us for the algorithm, helps us to know if you actually enjoy having the community office hours actually on YouTube itself. And I hope you like the effort that I put into this whole get up with everything around. It took me a little while to do, but for now I will switch to this. So yeah, if anyone's got any questions, you don't hesitate to put them in the chat, or if you have any remarks. I will stay live for maybe another 4 minutes, but it's getting quite dark here now, so I look like I'm like, because like if I put this light on, you can see the drop shadows. Like I look like I've you know, got bags under my eyes, and then if I do it like this, I look like I'm just a sweaty mess. I've been too long in the coding dungeon and I need to get out. But yeah, socials down here. Make sure you click the subscribe and like, please. I know everyone's like, oh, engagement, but it just helps us to know if you actually like this content being here. Okay, awesome. I will just double check if nobody has any questions on Discord. Nope, nothing. Okay, awesome. Right, thank you for tuning in, everyone. It's a lovely Thursday, and I hope you have a great tomorrow and even better weekend, which is what we're always looking for in this life. So thank you everyone for tuning in, and I'll see you in the next time.